Assalamu alaikum everyone. Welcome back to our discussion on Brayton Cycle. In the last class, we introduced the Brayton Cycle and solved an example problem of simple ideal Brayton Cycle. Today, we want to go ahead and talk about actual Brayton cycles and also look at different ways in which we can increase the efficiency of the Brayton cycle. So first, let's look at the different reasons which cause deviation from the ideal behavior that we considered in the last class. So when you talk about actual gas turbine cycles, they deviate from the ideal cycles due to two main reasons. First, because of irreversibilities that exist within the turbine expansion and the compression process within the compressor. And this is normally shown as the increase in entropy during the compression and the expansion processes respectively. So if the irreversibilities did not exist during the compression process, the ideal compression process would be isentropic. That is, S1 would be equal to S2, but that is not the case here. And that's because that's not the case in the actual scenarios because of the irreversibilities that exist within these turbines and compressors. The other cause for deviation is simply the pressure drops and the heat losses that exist. Now, the heat losses are typically negligible or pretty small in most cases. However, the pressure drops do exist in heat exchangers, in the pipings, and several components. And a simple example is the constant pressure heat addition, which was the ideal process that we considered for the ideal cycle. But for an actual cycle, the heat addition is not constant pressure anymore. There is a pressure drop that's going to happen as shown by this line. Same way there's going to be a pressure drop within the heat rejection process. So these are the different causes which bring the deviation between an ideal cycle and an actual cycle. Now, among these various causes, the major cause of deviation are the irreversibilities in the turbines and compressors. And we tend to handle them by defining the isentropic efficiencies. Now, the isentropic efficiencies are something that we have defined before, and I'm going to go through that rather quickly. So when you talk about the compressor, the isentropic efficiency of a compressor is the work input required for an ideal process divided by the actual work input. All right. So you have S2S minus H1 divided by S2 minus H1 or S2A minus H1. In most cases, we are given or we will be easily able to determine the value of H1 based on the temperature that is given, for example, the inlet temperature that is, and we are able to determine the enthalpy for an isentropic process by using the different relations that we have for an ideal gas undergoing an isentropic process. Now, in all such cases, the definition of isentropic efficiency allows us to calculate the actual enthalpy at the exit of the compressor. Same way, you have isentropic efficiency defined for the turbine in terms of the actual work output of the turbine divided by the isentropic work output. Here also, you make use of the isentropic efficiency to calculate the exact enthalpy that comes at the exit of the turbine. Now, the reason we want to consider the irreversibilities that exist in the turbine and the compressor is because they impact the overall performance of the gas turbine significantly. Now, the isentropic efficiencies or the irreversibilities that exist within the turbine, they end up reducing the work output of the turbine for a given pressure, for an expansion over a given pressure. Same way, the irreversibilities within the compressor, they increase the work input that's required to compress a given amount of gas over again the same pressure range. And therefore, the increase in the compressor work input required and the reduction in turbine work output that's obtained over the exact same pressure ranges that we are looking at causes the net power output of the power plant to go down. And therefore, to calculate what the exact power output is, we need to have a good idea about the isentropic efficiencies of both the compressor and the turbine. Now let's move forward and talk about how the gas turbines have developed over the years. Okay. Now, as I mentioned before at the beginning of this class, the whole idea has been to figure out ways to improve the thermal efficiency. Also, we want to ensure that the net work output per unit mass is higher, right? We don't want to compromise both, but at the same time, we want to figure out ways in which the thermal efficiency can keep on increasing with years. Okay. So the initial gas turbines were built somewhere in the 1940s. So that's about 80 years back from now. And I'm going to outline the three major strategies that have been used to improve the thermal efficiency over the past 80 years. The first and the most common approach is to increase the turbine inlet temperature. If you increase the turbine inlet temperature, that certainly goes up and increases the gas turbine efficiency. And the simple way this is achieving a higher efficiency is by increasing the average temperature of heat addition. So always increasing the turbine inlet temperature plays a huge role. Now let's look at how the turbine inlet temperatures have changed over the years. Back in the 1940s, the maximum turbine inlet temperatures that were allowed in the gas turbine expansion stage were somewhere around 540 degrees Celsius. So you could take in very low, relatively low temperature air and expand it within the turbine to produce the work output. Over the years, a lot of improvements in the materials and the manufacturing of the turbine blades involving the way they are cooled, the way they have cooling channels, and also the fact that we have been able to use ceramic coating on the turbine blades has allowed us to operate at much higher temperatures. So the turbine inlet temperatures as of now approach 1425 degrees Celsius. And I'm pretty sure they will keep going higher in the next few years. So this has been increasing the turbine inlet temperature has been the most common way of increasing the thermal efficiency of the gas turbine. Now, apart from this, certainly the other approach would be to increase the isentropic efficiencies of both the turbines and the compressors. Okay. Now, when we talk about the first generation turbine and compressors, certainly they had low isentropic efficiencies. There's no doubt about that. They're being built for the first time. People were getting power for the first time using this sort of a new cycle. And over the years, improvements in CAD as well as improvements in understanding of fluid mechanics and the way the computer simulations have progressed, it has allowed us to reduce the friction in a lot of these components and thereby reduce the irreversibilities that exist during the turbine expansion or compression within the compressors, and thereby improve the isentropic efficiencies to reasonably high values. When I say high values, we're talking about isentropic efficiencies reaching as high as 90%, 91%, 92% for turbines and compressors. Of course, this has happened gradually over a period of time, and this has been another way of increasing the efficiency. And when I talk about the increasing thermal efficiency of the gas turbine power plants, the manufacturers have used both approaches, increase turbine inlet temperature, but also figure out ways in which you could increase the isentropic efficiency. And the gains that have been made have shown up in the new generation gas turbine power plants, which have been installed in the last 20 to 30 years. Now, apart from these two modifications, the modifications which were more common in the earlier generation of the Brayton cycle was to simply add modifications to the simple cycle, right? Similar to the kind of modifications we have looked at when we were discussing the Rankine cycle. So what modifications can you add to the simple Brayton cycle? Well, the modifications are going to be similar in the sense that you can have regeneration, you can have reheat, as well as you can have intercooling. Okay, the efficiencies for low turbine inlet temperatures almost doubled when these modifications were incorporated into the design. And although these modifications tend to not exist in all turbine power plant designs, depending on the turbine inlet temperatures, they still continue to exist in older designs where the turbine inlet temperatures were slightly lower. And the reason why these modifications have worked sometimes, have not worked, or have not been implemented in others has simply to do with the economic cost of it, right? When you're making any of the modification, whether it's regeneration, reheat, or intercooling, the initial and the operation costs are going to be higher because you're having more components. So the decision on whether to have a modified cycle with all these components or whether to go ahead with a simple cycle, it's simply a matter of economics. It makes sense when the fuel costs are low. Well, it does not make sense when the fuel costs are low, certainly, but it certainly makes sense when the fuel costs are high, or when there's a lot of focus on the emissions that happen from gas turbine power plants. So for now, we don't see a lot of gas power plants with all of these modifications. We certainly see some of them with modifications, all right? But the major growth in the efficiency over the last 80 years has happened by increasing the turbine temperature. And this has by far taken care of the majority of the increase in efficiency that we have seen. Secondly, of course, the isentropic efficiencies of turbines and compressors have also helped, but the regeneration make sense when you're looking at smaller pressure ratios. At higher pressure ratios, it may not make sense. So the modifications that have happened to the simple cycle have happened in specific situations where they made sense, right? It's not a universal application that has happened that says that, okay, if you have a Brayton cycle, add these modifications and you will surely get higher efficiency. Well, you will get in a lot of cases, but not always. All right. So now let's move forward and talk about the Brayton cycle with regeneration. Now, when we talk about the gas turbine engines, well, the temperature at the exit of the gas turbine, or the temperature of the exhaust gases which leave the turbine, is most of the times much higher than the temperature of the air that's leaving the compressor. Let's see what I'm talking about here. So what I'm saying is the temperature at state 4 is much higher than the temperature at state 2. Okay, so if T4 is much higher than T2 right here, what this gives me is it gives me an opportunity to use this high temperature gases that exist from the turbine to heat up the exit of the compressor so that the temperature at the entry to the combustor is higher than T2. All right. So I want, instead of the entry point of the combustor to be T2, I want it to be slightly higher than that. And you can certainly do that by making use of the hot exhaust gases coming out from the turbine. Okay, this is the whole concept of the regenerator. So in a regenerator, what we do is, the regenerator is shown here. In a regenerator, what we do is we make use of the high temperature gases coming out from the exit of the turbine, and we use them to heat up the high pressure gases coming out from the compressor. And this eventually allows us to reduce the QN, or the amount of heat that you need to provide within the combustor, and thereby increases the efficiency. Okay, so when you use a regenerator, well, efficiency is going to increase in most cases, certainly as long as T4 is greater than T2. Now, how is the efficiency going to increase? Well, as I said, it simply happens because we are reducing the amount of QN. If you look at the TS diagram right here, the process from 2 to X, right? The heat increase from 2 to X, it happens simply because of the heat transfer from this hot fluid, and the hot fluid gets cooled down from state 4 to state Y. Okay. Now, this part right here from 2 to X is what can be written as QN regeneration. The rest of the part from X to 3 is QN. So as long as I'm able to push X a little bit higher, as long as Tx is greater than T2, and well, of course, this happens when T4 is greater than T2, I will be able to achieve the same network output with smaller values of QN. And if I can reduce QN, well, I can certainly increase the thermal efficiency. And that's the whole point of this regeneration business. Now let's look at it in terms of the efficiency formula. Okay, so again, here what we are saying is that for this regeneration to work, the cold side exit temperature, Tx, right, is always going to be smaller than or equal to the hot side inlet temperature, which is T4. Okay, this is certainly expected, right? The cold side exit temperature cannot be higher than T4 because the increase in temperature from T2 to Tx is simply happening because of the high temperature at T4. Now, we defined this parameter called regenerator effectiveness as the ratio of the actual enthalpy increase of the air that's flowing through the regenerator, which is Hx minus S2, divided by the maximum possible enthalpy increase. And if you think about the maximum theoretical possible enthalpy increase, well, the maximum possible increase would be if the enthalpy of the fluid at the exit of the cold side reaches H4, which of course is not going to reach, right? So this would be the maximum possible thing. An ideal thing which can happen in an ideal situation never happens in an actual situation. But we want to put this here so that we set an upper limit, okay? An absolute upper limit. So the regenerator effectiveness is simply Hx minus H2, which is the actual increase in the heat input, the actual enthalpy increase of the air going through the cold slide, divided by the maximum possible enthalpy increase. That's H4 minus H2. Okay. So when we talk about the effectiveness of the regenerator, we can certainly look at this for cold air standard assumptions, or when we consider the air to have constant specific heat. So here we can write it in terms of the temperature. So we're saying basically the effectiveness of the regenerator is equal to Tx minus T2 by T4 minus T2. And of course, we know that the Tx has to be smaller than or equal to T4, right? In almost all cases, Tx is smaller than T4. It's not even equal to T4. So when you use this formulation for determining the effectiveness of the regenerator, we can write a formula for the thermal efficiency of the Brayton cycle in terms of T1 and T3, which are the minimum and the maximum temperature within the cycle, all right, and the pressure ratio Rp raised to K minus 1 by K. Now, this specific formula for the thermal efficiency is not applicable when you do not have a regenerator. This is only applicable when we have a regenerator, okay? And as we can see here, the thermal efficiency is not just a function of temperature, but also depends on the pressure ratio, okay? And the reason it depends on pressure ratio is pretty obvious. If the pressure ratio is very high, there may be a point where T2 becomes greater than T4. And when T2 is greater than T4, it makes no sense to have a regenerator, okay? The heat transfer occurs in the opposite direction. So the thermal efficiency for a Brayton cycle, when you have a regenerator, certainly depends on the pressure ratio that you're operating. And regeneration makes most sense when you're dealing with lower pressure ratios, okay? At high pressure ratios, well, it may not make a lot of sense considering the economic cost involved for installing this. Now, when we talk about regenerator effectiveness, which is what we were dealing here, well, the values for regenerator effectiveness typically vary between 60 to 80%, depending on how well the heat exchanger is designed. And whether we decide to have a regenerator or not, it's mainly an economical decision, right? You have to see the you have to see if the economics make sense, considering the pressure ratio that you're dealing with. And first of all, whether the regenerator makes sense from a thermodynamics point of view as well, right? We need absolutely T2 should be smaller than T4 for a regenerator to make thermodynamic sense. So there's again a very nice example given in the textbook 9.7. So you can go through that. Here, the only new concept involved is the definition of regenerator effectiveness. I'm not going to solve individual problems for each of these cases where we add one modification at a time, but we're going to solve a problem where we have all these modifications together. Okay, that's what we're going to do in the next class on Tuesday. All right, now let's go ahead and talk about all the modifications that are possible. So we said we want to talk about a Brayton cycle. Well, we just spoke about a Brayton cycle with regeneration. The other modifications possible are a Brayton cycle with intercooling and Brayton cycle with reheating. Now let's see when do these make sense and when do we actually do them. Now, if you recall, we said the backwork ratio in a Brayton cycle is pretty high. We are talking about backwork ratios of the order of 30 to 80% as well, right? And if you don't recall what backwork ratio is, it simply is the ratio of work input to the compressor divided by the work output from the turbine. And a high value of backwork ratio simply tells us that the amount of work input that we need to provide for the compressor, it's very high. Okay, so anything that can reduce the work input to the compressor while giving us the same work output from the turbine would always be welcome. And one way of doing that is what's called as the multi-stage compression with intercooling.